black holes are something I work on. I have a few of my PhD students are doing awesome research and projects around black holes. There's a lot of things happening. And in the past 10 years, there's really an increase in knowledge and experiments that have happened that have told us a lot about black holes in all shapes and sizes and how they're made and what they're made up of. So it's kind of been an exciting decade to study black holes. And I think the first thing to get around is black holes are not this made up thing. It is not something that we just say, hey, it's this thing out there we don't really know. That's it. We do know information. We do know things about black holes. We can see it. We don't know everything. That's like a lot of things in space. And there's a lot of evidence we have of their existence, how they grow, how they change, and what it's like. Now, we've never sent something into a black hole. They're too far away. It would take almost 500 million years for the Voyager probe to reach the supermassive black hole, Sagittarius A star, in the center of our galaxy. So it's not like we can just pop over and see what a black hole has. But a lot of it involves observations and experiments within our own galaxy and other galaxies. And that's kind of what we're going to talk about today. But we really have to start with the birth of a black hole. And in order to understand the birth of a black hole, we have to understand how a star lives and how a star dies. And there's lots of different ways a star grows. And ultimately, we divide stars into two broad categories: small stars and large big stars. And small stars are things less than 8 times the mass of our sun. Our sun is a small star. And these stars don't generally form black holes. What happens is they grow, they puff out into a red giant, and then they go into a beautiful planetary nebula, and this gas expands into space, collapses back down to form new stars, but then it's left with a white dwarf. And that's pretty much the life cycle of a small star. It's the big stars where we actually start to see and get black holes. These large stars puff out just like a small star into what we call a red supergiant. They then explode, and in that explosion is actually where these black holes are created. And sometimes we create a neutron star. And what actually happens is when a star explodes, you're releasing all of the energy of a star. And this is something I get to do all the time, is find exploding stars. And so, the equivalent of one exploding star is equal to 100 million billion lightning bolts. So imagine one lightning bolt. Now imagine 100 million billion of them. That's what happens when a star explodes. You're essentially igniting, you're detonating this star, and you're blowing it up. And that releases so much energy. It's so bright, and you can see it. In fact, this is called supernova 1994D in a galaxy about 50 million light years. And this little bright star at the bottom here is actually not just a star. It is an exploding star in this galaxy 50 million light years away. So it's brighter than all the other things in the galaxy. It's amazing to see how big and powerful these things are. And stars explode all the time. That's a cool thing. In a couple of weeks, we'll talk a lot more. Georgie will talk about exploding stars, and I'll talk a little bit about exploding stars and how we see them and what we use them for. But one of the things that happens in the big stars when they explode, as I said, is they create these black holes. Now, and ultimately, what's going on the inside of a star? So if you imagine a star as an onion, and at the inside of the onion, at the inside of the star, you have a whole bunch of stuff being fused together. That's ultimately what creates the heat or the energy of a star. It's a big nuclear bomb smashing atoms together. And as you smash these things together in the inside, you build up pressure. And so that pressure starts to push outward. But you have a problem. You're building up more weight, more mass. So what do you build up more of? Well, you build up more gravity. So gravity is starting to pull it in. So gravity's pulling it in. So the star says, all right, well, in order to beat this, I need to burn more stuff to push outward. So it's this battle on the inside of stars between burning enough fuel so it doesn't collapse in on itself and enough fuel so it puffs itself out, but not so much that it burns too much fuel. And this is what goes on in the inside of a star, is this battle between pressure and gravity. And at some point, the star can't keep up this process. So much is happening. It's creating so much heavier and heavier, so many more heavier and heavier elements. heavier and heavier stuff. It's this added weight in the center. It can't keep it up. And what then happens is essentially gravity wins. Gravity starts to pull the inside of the star in. And this is what we call the collapse of a star. So we call these core collapse stars because the core, the inside of a star, collapses. So the way to think about this is imagine you take a scoop of dirt and you keep squeezing it and squeezing it and squeezing it and squeezing it until you can't squeeze it anymore. And that's ultimately what's happening is once this gravity is pushing it in, gravity just squeezes the entire inside of the star into a really tight ball. And the moment it stops doing that is the moment then when the black hole or the neutron star is created. And then the rest of the energy kind of, it's like your hand relaxes and it bounces off. So the star, this force rebounds and it travels and produces a shock wave through the star, causing the star to blow up. In fact, this is an animation from an observation that my group did using the Kepler Space Telescope. So you can see here it's in minutes. So we got the inside of the star squeezing. Oh, we're squeezing. We can't squeeze it anymore. And boom, there goes the shock wave and the star explodes. So when these big stars explode, we're actually seeing sometimes the birth of a black hole. And so the black hole is the squeeze inside. And in fact, most of the star ends up being squeezed into this. It's actually a relatively small amount of energy it explodes that we actually see. And someone's asked about how long do black holes live for? Well, this is an interesting question. We're going to talk about it because black holes tend to change over time and they grow and get bigger. And they last because they're not dependent on burning light anymore, doing this process. They live for billions and billions and billions of years, much, much longer than the stars that actually create them. So we've had the star collapse in on itself. We squeeze the inside so much, we squeeze it into a giant ball. Now, sometimes this is squeezed into what's called a neutron star. Now, a neutron star is essentially the leftover atoms, the bits of the atoms, really, the neutrons, being squeezed into an area. And it's squeezed into an area literally only about 20 kilometers wide. So something about the size of a city. And yet we've squeezed almost 1 to 2 times the mass of our sun into the size of a city. So imagine taking our sun and squeezing it into the size of Canberra, Sydney. That is a neutron star. It is such a dense thing. So imagine you have a spoon. And if you're to take a spoon and you scoop off the sun, that teaspoon rather, of sun would weigh about 5 grams. So if I take my teaspoon and scoop the sun, it weighs 5 grams. If I scoop the neutron star, it weighs 5 billion tons. These things are incredibly dense. But if you get enough squeezing and enough pressure, and enough squeezing and enough force inside, and there's enough mass, you get a black hole. And so there's actually types of black holes. We generally have 3 categories of black holes: stellar mass black holes, intermediate mass black holes, and supermassive black holes. And stellar mass black holes are really the birth of these black holes. This is where the life cycle of a black hole begins. We squeeze the inside in it, and it explodes. And someone just asked what happens to stuff that gets sucked into the black hole. We're going to talk about that in a bit, what actually happens at that point, because it's some cool things. Now, we have 2 black holes here. So here we have one black hole over here and another. And these are what we call stellar mass black holes. So these weigh anywhere between 20 and 50 times the mass of our sun. So they're bigger than our sun, but they're not gigantic. They're not like the big ones we see in the center of our galaxy that we'll see in a second. And a lot of the discovery and our knowledge of these black holes has only come about in the past 3-5 years. And most of it's come from what we call gravitational waves. So this is something called LIGO, and it's a big gravitational wave detector. So it's a really cool special instrument. And you see it has these 2 long arms. So it's this big long tube here that's over 4 kilometers, and another one here that's 4 kilometers. So it's like a shape like an L. And what this instrument does is it has a big laser at one end and a giant mirror at the other. So it shoots the laser, hits the mirror, and the laser bounces back. Now, the cool thing that happens is sometimes, like here, these black holes actually collide and merge together, that they actually grow together. And what happens is they produce a ripple in space. And what this thing does, LIGO, this gravitational wave detector, is if the laser bounces off the mirror and comes back, it should always come back at the same point. It's going down a long tube. It's like looking in a mirror. You should see your reflection exactly where you're looking. But if a big wave, what we call a gravitational wave, comes through space, it actually wobbles. It actually shifts the Earth. And that means if the shifting happens, the light doesn't come back at the same point. We actually can see the wave coming through space. And there's a few of these detectors now, two in the US, there's one in Europe and another one in Japan now. And what we can use this is to see how these gravitational waves hit the Earth. And this is actually what it looks like. This is an animation of what it looks like. So we have two black holes and they're kind of bouncing and merging in around. And as they collide and they grow together, they produce these little ripples of space. So imagine space as this giant sheet, and you plop something on that sheet. It creates a little wave. Imagine you're standing out on a pond or a lake and it's perfectly still, and you drop or you throw a rock. That will create a ripple and it'll go through the lake, it'll go through the water. And in this case, the lake, the water, is space-time. It's literally the fabric of the universe. It's where our Earth is sitting in. And these waves travel through space and hit our Earth. And this big thing that's 4 kilometers by 4 kilometers can detect these very small waves. And when these waves happen, our Earth does move, but it moves by such a small amount. We're literally talking about smaller than a human hair, about the size of a proton in some cases. So it's not like we're wobbling around. These are really small movements, but they are caused because these things are so massive and they have so much gravity, they warp, they bend space around it. The gravity bends space around it. Now, someone's asked, how big can a black hole get? And this is where it gets interesting. What we've been able to see is now LIGO and a whole bunch of other detectors working together have been able to see lots of these. And they all have different waves, so it all depends on how big a gravitational wave is. So it all depends on how big the black hole is. So you can see here, if they're about the same size, that merging, that wobbling happens quite a bit. If you get one really big to the other, it's just a really small boop. And sometimes you get these really big waves that we can see. Now, the cool thing is kind of the power of the wave. We can use it to figure out how far away it is and how big, how massive the black holes were that created it. And so you can see here's some examples. So these two black holes weighed about 35 and 30 times the mass of our sun. And then they merged together, they grew together. They did that colliding, they produced that wave of gravity through space that we detected here on Earth. And now it produced a black hole about 62 times the mass of our sun. And there's been a bunch of other ones. We've seen these ones that are 8 and 15 producing only 20 times the mass of our sun. And so we've seen some small ones, we've seen some big ones. We see a whole big range of these black holes. And what we think happens is these collisions keep taking place. They keep growing together. So these black holes keep colliding and they keep getting bigger and bigger and bigger. And this is when we start to get into what we call the supermassive black holes. And we're going to talk about that in a second, because that really tells us how big a black hole can get based on what we see. So these stellar mass black holes are never millions and billions of times of the mass of our sun. They only are, the tens to hundreds of times of the mass of our sun. And now that we can detect their collisions, not only do we know they exist, but we can see them grow. And we think these black holes keep growing and growing and growing until they get bigger and bigger and bigger. And then we get the big ones in the center of galaxies, the supermassive ones that we'll talk about in a second. But one of the other cool things is we don't just detect black hole colliding. We sometimes collect other collisions. And so this is kind of a nice graph of seeing, or a nice image, a way of seeing all the different masses of black holes. So we see our black holes that have collided up here. So on the left here is the mass in terms of how big it is the sun. So that's 1 times the mass of our sun, 2, 5 times the mass of our sun, 10, 20, 40, 80. And so you can see that down here, there's this area that we call neutron stars. Now, what we've also been able to detect is neutron stars colliding. So neutron stars are also really dense. It produces not a lot of heat. It does have energy, and it does rotate. And what we've now detected is sometimes these neutron stars collide. And when these neutron stars collide, they produce bursts of energy, bursts of light that they shoot in big jets. And we call these jets sometimes gamma ray bursts. And they shoot off gamma rays. So kind of it's a different type of light than we can see with our eyes. So imagine we have X-rays. Well, gamma rays are even harder and more energetic than X-rays. So we can't see them here with our own eyes, but we can detect them in space. And as these neutron stars collide, they do bursts of gamma ray light. So we can see their collisions. But because they're also quite heavy, if they're close enough, we can also detect their gravitational wave, their ripple. And this happened in 2017. A Fermi, which was a satellite looking in gamma rays in space, saw this big burst of gamma ray light right over here. And at the exact same time, what LIGO, this gravitational wave detector, saw was this burst of something colliding in space and producing a ripple. And it happened at the exact same time. And so the cool thing is, not only do we feel the ripple through space, but we also saw the burst of light through space. So that's kind of one of the signs that we know these neutron stars also exist. There's a bunch of other ways, but it's how we also know that our measurements of black holes colliding are correct, because they're different than when we see neutron stars colliding. So we've also we've seen and detected a neutron star colliding into a black hole. So all these different cool combinations of big things smacking into each other. And it tells us a lot about these small, massive things, really these small black holes. And in fact, with this neutron star, we also saw the explosion. This is taken from a telescope in Hawaii and this one in Chile. And so you can see in this galaxy, there's nothing there. And all of a sudden, in 2017, at the same time, this other explosion happened, and this ripple, this new star exploded. So we can see the explosion of the neutron stars. The whole bit blows up, and we can see the light coming from it and the wave traveling through space. Let's get back to black holes. So how big can a black hole get? Well, we know that in the center of our galaxy, there's a supermassive black hole that weighs about 4 million times the mass of our sun, or 10 to the 33 elephants. So a lot of elephants. So what we're seeing here is a time lapse. So this is taken from a telescope in Chile, at the Very Large Telescope, and we're staring at this little point in the middle here. And you can see the stars moving around it. There's something in the center here with a lot of mass, a lot of gravity, causing these stars to swirl around it. And again, this time lapse is taken over 20 years. So it's not like you can see this in the course of a night. You have to keep taking images and images and images at the exact same point and see how the stars move. And what we can tell is that based on how fast and how different the stars move around this area, we can measure the strength of this black hole. And we think, and we've measured that this black hole, what we call Sagittarius A star, the supermassive black hole in the center of our galaxy, weighs about 4 million times the mass of our sun. So if you think about it, those black holes we were just talking about weigh 10, 30, 80, maybe 100 times the mass of our sun. And what we think happens is you just keep growing and growing and growing until we get the intermediate mass black holes, the ones that weigh 10 to 50,000 times the mass of our black hole. And then those start to collide, and they build up to be these supermassive black holes. And in the center of every large galaxy, we've detected and measured that we think there are these supermassive black holes there. So in the center of all these big galaxies, these supermassive, these big black holes exist. And we've detected all range of sizes, and we're going to focus on one galaxy in particular in a second. But a few people have asked questions related to this. Let's look at what's happening at a black hole. So this is a supermassive black hole. So we have the singularity. Now the singularity, don't worry about reading the words, but you can if you want. The singularity here is the point where not even light can escape. So the gravity, the pull of the black hole is so strong that not even light, traveling at the speed of light, 300,000 kilometers a second, can escape it. And what happens is that this light, as it goes in, we can't see it anymore. It kind of stops. And there's so much gravity at the singularity that it creates what we call this event horizon. And the event horizon is that boundary between going into the black hole and not. It is the boundary which is the last point you can see things around the black hole. That is the point where essentially light stops. Now, if you were to fly into a black hole, what would actually happen? Someone asked this. Well, the process is called spaghettification. And that is the gravity of the black hole starts to pull you and pull you and pull you and pull you apart. And I'll show you this in a second. We haven't done this in person, but we see this happening to stars, that the black hole starts to rip you apart. And as it starts to rip you apart, it stretches you. And some of you end up swirling around the black hole in what we call the accretion disk. So the accretion disk is essentially, it's kind of the leftover bits of stars and gas that have gone into the black hole, but some of it has been thrown around. So some of it's slowly going towards the black hole, but some of it spins off and shoots in these big jets. So the black hole's spinning around in space. So you can imagine as stuff is falling in, some of it is shot off into these big jets. So there's lots of ways we can detect the activity of a black hole. We can see the things swirling around it, the accretion disk. We can see the things essentially shooting off the black hole in these jets. And we can see things actually falling into the black hole or being ripped apart by the black hole. Now, the black hole also does something funny. It changes time. And that is because if you change the space around it, space and time are the same. You change the time around it. It's what we call time dilation. You can literally warp, change the shape of time. And so as you go into the black hole, time actually slows down for you. So if I were to throw you into a black hole, besides dying and turning into a giant piece of spaghetti, but let's not focus on that, you would look out and it actually wouldn't look different for you. You would appear to be moving normally through time. It would be like a year, 100 years, whatever your lifetime is. But if you were to look out of the black hole, everything would be moving super, super, super fast. You would almost see the universe evolve in billions, hundreds of billions of years. So you would actually see the universe change almost in an instant. And so in your lifetime, the entire universe will change. But from us on the outside, you look like you're moving very slowly. That was my internet. That was the black hole. You would almost appear frozen in time. So not only are you a giant piece of spaghetti, but you're a frozen piece of spaghetti. And so this is quite an interesting thing, is we're actually limited at the point of understanding black holes. We can't see inside the black hole, what we call the singularity, because we can't see the light. We can't see things coming from it. We can only see at the boundary, what we call the event horizon. And someone has asked this, if a black hole space around it seems bent like water in a glass, is it liquid? So ultimately, yes, the black hole does bend space and time. Anything with gravity bends space and time. The Earth does. So it's less like water, and it's more just kind of like a giant invisible sheet. That's ultimately what our universe is it's not a liquid, but it does stretch, it changes, it can be manipulated. And that's a great thing, that gravity, anything with gravity, the moon, Earth, or black holes all do this. It's just the more gravity you have, the more mass, the bigger the effect. And since black holes weigh a ton, literally, they have a lot of this effect. Now, what happens when a black hole dies? Well, this is interesting, and we're going to talk about this in a second. So we've actually detected black holes ripping apart the star. So you might be able to see here, it's on purpose. There's a little black hole here. It's kind of right here right now. And we're going to have a star come near it. So this is of an object called Assassin 14 Li. And as the star gets too close, the black hole starts to pull off the atmosphere of the star. It starts to suck it around. So we start to see that accretion disk form, and some of it is actually spit back out. So the cool thing is as the star starts to fall into the black hole, we can see it being disrupted. We can start seeing it pulled apart. We can see bits of it being shot off into these jets. And we can see the black hole really essentially kill a star. Now, what happens when there's a lot of stuff near it? Well, the black hole keeps feeding. So if there's a lot of stars and a lot of gas near a black hole, like here, it will keep sucking and sucking and ripping apart. And so it'll keep growing, and the accretion disk will keep spinning around. But if there's not stars and gas near it, the black hole doesn't really have an accretion disk. In fact, if we go back to ours, this is looking towards the stars at the center of our black hole, the center of our galaxy near our black hole. We don't see that. Our black hole is kind of quiet. There's nothing falling into a black hole. Now, scientists have actually detected bursts from our black hole that happened millions of years ago, but right now, nothing's really happening. Sorry, someone just asked if we ever try to put a camera in a black hole or an object, would it become spaghetti too? Yeah, a black hole will destroy everything. So the cool thing is, if the camera went in, if we sent a satellite into this black hole, not only would the satellite be stretched, but because time, the video would be moving in slow motion. So, and then eventually be destroyed. So there's no escaping a black hole. And so we get to see when these stars collide with it. And it's a really cool way of confirming that as something gets too close to a black hole, the black hole will rip it apart. And it only takes a certain point right where that gravity can take over and literally suck off that star, that atmosphere of that star. Now, someone just asked, and this is quite interesting, how many black holes are there? And especially in our Milky Way. So there's more than one black hole in our Milky Way. We have the supermassive black hole, and we also have millions of stellar mass black holes, these small black holes. So we know there's actually a lot of black holes in our own galaxy. And there's a lot of galaxies in the universe, which means there's a lot of black holes. Now, we're going to look at this galaxy. And at the center of this galaxy is called M87. So this is a neighboring, nearish galaxy. And the entire galaxy is here. But using radio telescopes like in Australia at Parkes, astronomers have been able to see these big jets shooting out of the black hole. So this is essentially radio light. So imagine being able to hear it like a radio frequency. Well, stars emit radio light as well. And this is the gas, most of it's hydrogen, being ripped off stars and other things near the black hole and shot out into the space. So you can see here, this is the entire galaxy, yet what we call these lobes, these areas leaving the black hole, are gigantic, bigger than the galaxy itself. And you can kind of even see a little bit of the wave pattern almost, like it's bursting, like it's blowing out into space, because that's actually what the black hole is doing, that it's spurting out all of this stuff into space as the stars or gas gets near it. And the Hubble Space Telescope looked even closer at M87, and you can see even in the optical colors, the colors we can see with our eyes, there's this little bit of stuff leaving the jet, leaving the center of that black hole. So that means there's stars or gas or things near it shooting out from the black hole. And someone actually just asked, how can this jet leave the black hole? And that's because it never enters the black hole. So if, again, we go back to this little diagram here, this stuff is swirling around the outside. So black holes are not circular, they're balls. Imagine a sphere, imagine a ball. And that ball is spinning around in space. And as the stuff comes around it, it hits the surface and is shot off out from the black hole. So it never actually enters the black hole. It kind of bounces off the black hole. So that's how these things escape, and that's how we actually detect them. So it's stuff that never falls into the black hole. Now, the cool thing that's recently happened is M87, this galaxy, has been studied in lots of different colors. So a radio telescope in the US, the VLA, so looked at the center, and you can see, again, all of this gas. So look at this scale. This is over 10,000 light years across. So this is gigantic in terms of the area we're looking at. All of this gas, this hydrogen gas being shot off. And they looked at it even closer, and this is on the scale of across here is about 6 light years. So imagine this 6 light years across. That is even further than the nearest star to us than the sun. So Alpha Centauri is only 4.2 light years away. This is gas shooting out of that black hole. And then the Event Horizon Telescope zoomed in on this area to take a look at it. Now, the Event Horizon Telescope is a really cool project. And what they did is, they used radio telescopes all around the world, and they synced them. So they treated it as one big telescope. So imagine, instead of your eyes close by, they were really far apart. And this allows them to get a really clear image. So they can't see necessarily further, but they're able to see clearer of the things close by. So it's like having a telescope the size of the world, the diameter of the world. So instead of having a radio telescope 100 meters wide, they have a radio telescope 12,000 kilometers wide. And this allowed them to look at the inside of M87. And this is, in fact, a real image of a real black hole. And in fact, if you want to learn more about this whole process, Adam on Monday on the Mount Stromlo Facebook page will be talking about it, because he doesn't do it for this, but he uses this technique to look at stars up close. So it's a really cool technique we call it interferometry, and Adam will talk a lot about that. And what you see here is this stuff around the inside, this big, bright donut-looking thing. That's the accretion disk. That's where all that gas and stars is being swirled around. And you see kind of the black hole in the center. That's a black hole. That's the black hole. This is the boundary. That is the event horizon. That is the boundary that not even light can escape. And as the things are falling in, it's being shot off into these giant jets. And so this is really cool. So we're not actually directly seeing the black hole, because of course it doesn't emit its light. It's like seeing a silhouette. It's kind of on top of the accretion disk, and it's blocking out the light from behind it. It's creating kind of like a shadow, a silhouette. And this is how we can actually now directly see black holes. And this is a cool one, because if we go backwards, let's go backwards. Here's the center. Here's the accretion disk. Here's all that stars and gas swirling around it. We can see it then shooting out into space with these big jets, and the gas keep going and going and going, and even producing further out from the center of the galaxy and even further out into space. So we can really put together the picture of actually what's happening with this black hole using lots of different telescopes and lots of different techniques. And this is the same black hole that started off as a stellar mass black hole billions and billions of years ago. Now, to put this into scale, though, how big this black hole is, I like this image from XKCD. So it's a comic, but what we see here is that's the sun, that's the orbit of Pluto, and that's how far what we call the Voyager probe is. So that's to scale how big it is. So essentially, this black hole is bigger, 3 times bigger than our solar system, and yet it weighs over 1 billion times the mass of our sun. It is literally gigantic. And it's a really cool thing to be able to actually see the effect of the black hole and what's happening with the black hole. Now, one of the things that's always been questioned is what's actually happening inside the black hole. Now, of course, we can't see. We've never been able to go into a black hole. And if we did, we wouldn't be able to escape. Some people have even hypothesized that maybe black holes are something like wormholes, that if you go into a black hole, you would pop out somewhere else in the universe, or maybe even another universe. And so the idea is, if you're to go in this black hole, here we have a black hole in the center here, and it's actually acting as a magnified tunnel cutting through space. You might have seen this in the movie Interstellar, where, in fact, fun fact, to create the black hole and the wormhole in Interstellar, they created a model so accurate, we actually made a cool discovery. It is probably the only movie that not only has published a scientific paper, but the producer has won a Nobel Prize in Physics, Kip Thorne. What they realize is, as things go into a black hole, because that black hole, again, is a ball, imagine it like a balloon. So as a thing goes into here, the balloon squeezes. So it bulges out the other side. So the black hole actually bulges as things fall into the black hole. And that's because, again, it's not a circle, it's a ball in space. Now, wormholes may exist, but we don't have any evidence of it. And in fact, someone has predicted that, right, if things are going into a black hole, a wormhole, and they pop out somewhere else, well, they should pop out as white holes. But we've never found pockets in space where things have been popping out of it, that we never have detected these things. So we don't really think necessarily that's happening. And because we've seen black holes merging, we've also seen these mergings of black holes happen in the scale of galaxies. So when a galaxy collides, the massive black holes, these supermassive black holes in the center of the galaxies, spin around and ultimately merge together to create an even bigger black hole. Now, there's been a lot of questions, so we're going to try and take some. Now, someone asked, essentially, how does a black hole die, and how long does it live for? This is an interesting question. A black hole eventually, something called Hawking radiation, it slowly leaks, seeps energy, radiation out into space. Very, very small amount. So a black hole actually does require things to go in it, essentially things to feed it. Now, kind of like a black hole or like a dog almost, it could keep eating and eating and eating. And even though it's still hungry, it will still eating some more. And we've detected black holes in galaxies we call quasars. So quasars are galaxies really far away, billions and billions of years ago, that have a big black hole that's dominated by a black hole. And they appear to be eating faster than we planned, bigger than we planned. And so there's a lot of questions about how quickly the black holes grow and how much stuff they need. But if everything disappears in the universe at some point, or a black hole becomes isolated and it has nothing to fall into it, over billions and billions of years, we're talking about 100 billion years, the black hole eventually stop, and then it'll eventually fade away. But this is on the scale of almost probably longer than the universe. So eventually a black hole will go away. It just takes such an enormous amount of time. And in between, it is more likely that things have come near it, and more importantly, other black holes have come near it and they merge together to form an even bigger black hole. So we think black holes keep swallowing others. And in fact, the Andromeda Galaxy, which is a neighboring galaxy to us, it's about 3 times the size of the Milky Way. We will collide with Andromeda in not for a long time. And as those galaxies merge, the 2 supermassive black holes will merge together to form an even bigger black hole. So we think it keeps happening and that the black holes keep growing. Can a black hole move around in space? So yeah, black holes do move. Now the supermassive black holes tend to end in the centers of galaxies, but the stellar mass black holes are all over a galaxy. So stellar mass black holes can be all over the Milky Way. We haven't detected anywhere near the Earth. We don't think there's many near our solar system, if that. So it's not like there's any danger to us, but they can move and they do exist all around a galaxy. So what happens if a black hole sucks in a planet? If a black hole sucks in a planet, it's a similar thing to what happens if a black hole sucks in a star. It will rip that star apart and it will spit it out. And people have detected what they think are some types of brown dwarfs, which are kind of like failed stars, falling into black holes as well. And in fact, those stars, if they have planets around it, which they probably do, all of it will get sucked in, and so all of it will get ripped apart. So black holes are easy ways to destroy entire solar systems. Now, again, luckily, that's not going to happen to us because there's nothing near us, but it's cool to see this process happen. And it's also cool to see black holes being active and really changing things. And we can see black holes go from being quiet to really active. So we can see black holes that didn't have anything going on or swallowing anything to all of a sudden giving bursts of light and energy shooting out into space. So we can see the activity of black holes in real time. Someone said, how do scientists find out this much info about a black hole? I think this is a really good, important question. How do we know about this? And this is because we do different experiments. We do the science. We can't do the same observation or the same experiment or answer the same questions all the same way. So we need to build different telescopes to directly image it, or detect its gravitational waves, or to see the thing shooting out it. So they all require different ways of looking into space and sharing that information. So someone, we'll say, hey, we detected this black hole has spurted out this much energy, this much gas. And so someone else can look at it in a different color and light and see, was there anything that came out of that black hole before? Or is there anything else coming out of that black hole? So it's kind of like putting a jigsaw puzzle together. We have lots of different pieces, and we have lots of different pieces that fit together. It's all about a matter of finding the pieces and then finding how they go together. And in the past 10 years, a lot of this has happened with our understanding of black holes. Now, someone asked how far or how big is the biggest black hole? The biggest black hole we know of is at least 6 billion times the mass of our sun, 6 billion. So these things are giant. They think they could be even bigger. One of the big questions as I was talking about is, how do black holes get so big so early in the universe? When we look back about some of the very distant galaxies, they have these really big black holes. And if black holes take time for the stars to explode and collide and merge together and all that sort of stuff, how do they get so big so early? That's a big area that we're trying to understand. is how do these black holes grow, and how do they grow so fast? So theoretically, eventually everything. So someone asked, so if everything ended, if everything will get sucked into a black hole at the end, would there be one massive black hole, nothing else? No. And that's ultimately because space itself is growing. So the universe is growing and things are getting further apart. So local areas in the universe, so the galaxy or galaxies, will eventually grow into one black hole, and those black holes will merge. But as the universe expands, those black holes are getting further and further apart, so they won't all grow into one giant, massive black hole. If the universe, what people thought would happen 20 years ago, collapsed in on itself, that it came together, that could happen, but that doesn't appear to be the case, that the universe will just keep growing. And in fact, it's growing faster and faster. And in fact, in a couple of weeks, I'll be talking about what we know about this and how the universe is growing and how the universe may end. So we'll have a whole big discussion on that. We'll take 2 more questions. And then if you have any more questions about black holes, feel free to type it in the chat and we can answer it after. Again, there will be talks later this week on the Mount Stromlo Facebook page. On Friday, you can actually see we'll be doing a public stargazing night. I'll be running the stargazing if it's clear. Right now, we're having lots of rain, and it's still rain predicted to Friday. So we'll see what we can do. But there'll also be some amazing talks to tune in. And next week, I'll be talking about space exploration, how we're moving, how things are growing, and just some of the really cool things happening in space and space technology. What happens when a black hole dies? And again, this is an interesting question of, we don't know what's inside the black hole. So when the black hole stops feeding, when it stops things coming into it, what happens with that? Well, eventually it loses mass, it loses energy, and then it kind of just stops. What that singularity is, so that singularity is that point in space where things are going to, and the event horizons around that, and the accretion disks around that. We don't really know what actually happens, because we'd have to kind of know what happens inside a black hole, and we don't. So it's an interesting question, ultimately. What is the future of black holes? We can see them growing, we can see them evolving, we can see them being, but what happens in the future, we ultimately don't know. And so a couple of people have asked, what is, or how many black holes are there? There's a lot. So we think every big galaxy, and there's hundreds of billions of large galaxies in the universe, has a supermassive black hole. And then we think all those galaxies have smaller stellar mass black holes. So, there's literally billions and billions and billions of black holes in the universe. And there's millions of black holes probably in our Milky Way. So black holes are really more common than you think. And we're really just now understanding a lot about them. And that's going to keep growing. We're going to keep understanding more and more about black holes, and they'll become less mysterious, but also more entertaining. And I think that's the cool thing about understanding it. And when we do projects, look for supernova, we find new black holes all the time, because we can see that burst of light. And so there's a lot of cool projects we're doing here in Australia that will answer some of these bigger questions. So I think that's it for today. If you have any more questions, feel free to type it in the Facebook Live video. I hope you enjoyed the talk about all things black holes. Have a good day and a good week, and don't get sucked into a black hole. See you next time.